And we're back. So let's take this and apply it to continuity. So the question is, okay, what's continuity? And if we're kind of thinking about it in everyday language, or just sort of thinking, how would I describe this easily? The idea is that a function's continuous if you can draw it without lifting your pencil. Now, what we mean by that is, if I try to draw a function, I'm just going to, bear with me a second, I don't want these here. So I'm going to get rid of them. If I draw most of the functions we're used to, let's say I draw, here's a sine curve, for example. That's continuous. I can draw it without lifting my pencil. If I look at tangent, just as an example, tangent kind of goes along for a while and is continuous for a while, but then it jumps to infinity. And there's an asymptote, right? And once the asymptote happens, I have to jump down here. And I have a problem then because wait a second, I can't draw this without lifting my pencil because I can't come from up here and go back down there. So that's one type of discontinuity, is you can have an asymptote. And if you have an asymptote, you can't cross that, so you have to lift your pencil. Another example is if you have a point of discontinuity. You guys are used to rational functions. If I was drawing and I just said, my curve looks like this, and then right here there's just a point of discontinuity, and then it just keeps going up. Okay, so let's say, so if that happens, I can't draw that without lifting my pencil. Now technically I can, because I can come along here, go around the circle, back, and go up. Okay, but the idea is that you would have to, if you were just drawing and then you skipped a point, instead of drawing it like an open circle, you'd have to go lift your pencil and come back. So that is another point of discontinuity. So there's an asymptote, that's one type. There is a point of discontinuity. And the other type of discontinuity we can have is you can have a break in the function. So that means a piecewise function looks kind of like this, and then I color that in, and then I jump down here and it kind of goes up like this, let's say. So there's actually a break. That's the third type of continuity we're going to see. And again, I can't draw that without lifting my pencil. I've got to draw it, I can color that in, and then I got to jump down here, so I've got to lift my pencil. So that's the idea. And each of these happens in different situations. So asymptotes, you've seen them in rational functions, and you've seen them in tangent and cotangent and secant and cosecant graphs. So you've seen them in a few different places, but that's what an asymptote is. We've seen points of discontinuity with rational functions, and then we've seen breaks just in our last video. Just in the previous example we did, we've seen breaks with piecewise functions. So that's the kind of common definition, but what does it actually come out with if we talk about it in mathematical terms? And here's what the definition of continuity actually is. A function is continuous if it satisfies three conditions. First, the function has to exist, which seems like an obvious statement, and it is, but it has to be there. If it's not there, it's automatically discontinuous because it's not there. So a point of discontinuity would fail rule 1, right? Because the function's not there. It just drops out. And that's why it's called a point of discontinuity, right? It's called a point of discontinuity because it's a point of discontinuity. It's where continuity isn't there. It's broken. We didn't really understand the concept of continuity when we talked about a point of discontinuity, so we didn't really formalize it until now, but that's what it means. So if you have a point of discontinuity, that breaks down. The next thing is, not only does the function have to exist, but the limit also has to exist. All right, so the limit has to exist and the function has to exist. If those things are both true, then we jump down to this, which is that the limit as x approaches a has to equal f of a. So the quick way to remember it, and the way I remember it, is the function has to exist, the limit has to exist, and they have to be equal. That's how I say it, and that's how I remember it. And different discontinuities break different rules, but they go in order. They're a hierarchy. So in other words, if the function doesn't exist, you don't have to check the limit. even if the limit does exist, because the function doesn't. So you're done. If the function exists, then you go to the next step, which is to say, okay, if the function exists, then the limit has to exist. And if that is also true, great. If it's not true, then we're done. We say the limit doesn't exist, we're done. It's discontinuous. If it does, then we can say, okay, is it equal to the function? And if it is, then we can say it's continuous. All right. So we're just going to do one example, and then we're going to practice some more in class. But here's an example. This is a piecewise function. Okay, so there's three pieces to it. It's x between 0 and 1. It's x minus 2 when it's between 1 and 3. And it's x minus 4 when it's between 3 and 4. And then it stops at 4. So it starts at 0, stops at 4. But you'll notice there are two places where it switches function. So in other words, it switches from being x to x minus 2 at 1. And it switches from being x minus 2 to x minus 4 at 3. And those two places are possible discontinuities. Because inside each domain, we have continuous functions. We have lines, right? We have x minus 2, and x minus 4. They're all linear. And lines are continuous. So we just have to say, if it's going to be discontinuous, it's going to happen here, where it jumps from x to x minus 2, or it's going to happen here. Okay? So let's just look at, is it continuous at 1? All right, so we're going to look at this jump first. So first rule for continuity says it's continuous at 1, first of all, if f of 1 exists. Okay, so when x is equal to 1, it's x. So I say f of 1 is 1. That is true. It works. It does exist. So then I go into the next rule. The next rule says the limit has to exist. I go, okay, if the limit exists, I need to look at two functions. I have to look at the function when x is less than 1, which if I scroll up here is x, and I have to look at the function when x is bigger than 1, which is x minus 2. So if you look down here, I'm looking at the left-hand limit, which is x, plug in 1, and I get 1. I'm looking at the right-hand limit, which is bigger than 1, so it's x minus 2 is the piece of the function I'm talking about, again, because when x is greater than 1, f of x is x minus 2. And when I do that, I plug 1 in and I get minus 1. So that leads me to the conclusion that because these limits are not the same, and this is what we were talking about just in the previous video, just in the last couple of examples before we get into continuity, if the left-hand limit and the right-hand limit are not equal, then our conclusion is the limit does not exist. And if that's our conclusion, then our answer to the question, is it continuous at x equals 1, is no, the function is not continuous because the limit doesn't exist. Okay? So that's how you check to see if something is continuous. If you look at the other possibility, the 3, okay, and we'll just do this kind of up here. First of all, when x is equal to 3, so I'm going to do this in red pen, and I'm just going to do it up here. So first of all, f of 3. What's f of 3? So I go, okay, f of 3, that comes when x is equal to 3. It's described by this. So it's 3 minus 4, and that's minus 1. Then I look at the limit. So I want the limit as x approaches 3, and first of all, I want the limit as x approaches 3 from the positive direction. So when I look at that, it's when x is bigger than 3, it's x minus 4. So I go 3 minus 4, and I get minus 1, which is the same as I got up there, which it should be. Then I'm going to do the limit as x approaches 3 from the left, or less than 3. That is this function, x minus 2. So I get 3 minus 2, and that gives me 1. These are not the same, so I can conclude that the limit as x approaches 3 of f of x does not exist. Well, does not, there we go, does not exist. And because of that, we can make the statement that it's also discontinuous, and I won't write the whole thing out, but it's discontinuous at 3, all right, because the limit doesn't exist. So all we have to do whenever we check for continuity is look at, are there places where the function doesn't exist? And those are typically asymptotes or points of discontinuity, where the function's not there. if the function does exist, then we say, okay, does the limit exist? And if the limit doesn't exist, that generally means, again, that we're at an asymptote or we have a break. In this case, it means we have a break because x and x minus 2 are not at the same spot when we're at 1. So that's what happens there. So in terms of what we're looking at, if you look back at what I drew up here, we're looking at a situation like this when the limit doesn't exist, generally. The limit also doesn't exist with an asymptote, but the thing is that generally speaking, if the limit doesn't exist for an asymptote, we don't ever check it because the function doesn't exist. So we stop at that level. We don't go and check the limit. So generally speaking, if the function does exist and the limit doesn't, we're looking at this. Okay. And then the third rule is that they have to be equal. And so sometimes the only other thing you can happen is you can have a piecewise function that actually has a point of discontinuity in it, but then the function is defined somewhere else. The function has a value, the limit has a value, but they're not equal. That can happen. So we're going to go over a bunch of those in class on Monday. But that is how you talk about, that's what you do with continuous and discontinuous functions. If you can check continuity, you just have to check to make sure that these rules are satisfied. Okay? And if they are, great. And if they're not, it's discontinuous. So we're going to stop there. We'll do some questions, some practice questions, but that's continuity. So one thing we talked about, left and right hand limits, leads to another concept, which is continuity. When we're done talking about continuity, practice that a little bit, we're going to move into, okay, what do we do with, if something's continuous, how do we then use limits, one-sided limits, and this concept of continuity? Where does it all apply to this calculus question we're trying to answer, which is, what's the instantaneous rate of change at a particular point on a curve? That's what we're trying to answer. What's the slope of the tangent line of a curve? All right, so we're going to do that later. Right now, we're going to end the video and you can practice some continuity.